Okay, welcome to the second video. We're gonna solve now problem 55, and it states a load it's drawing 10 amps RMS when connected to a 1200 volts RMS supply running at 50 hertz. So we have a voltage source basically that it's powering a load of that it's consuming 10 amps RMS. If the source is operating at a lagging power factor of 0.9, so power factor of 0.9, lagging, so I wanted to clarify something. When we say inductive, it's actually the same thing as saying lagging. Okay. When we say the contrary, capacitive, we refer to leading. Okay. So both things are equivalent. So what do we mean with this? Let's say we have a voltage that is a reference. Same thing that we're going to do on this problem. It's the current. If the current is ahead of that voltage, let's call it I1, then we say that this current it's leading the voltage. What does it mean? It means that the circuit is capacitive. Right? And we're going to look on this problem that has a direct meaning with reactive power sign. So if some other current, let's say this one, it's behind the voltage, so it's lagging, that means this one is inductive because it comes from an inductive circuit. Okay, and this one is capacitive. So that's the picture that you have to remember. From now on, we're going to use inductive or lagging as a synonym, and capacitor or capacitive and leading as a synonym too. So we'll make sure that you revisit that. That is going to be your number one rule for power now. So the first question asks about calculate the peak voltage magnitude. Now from the previous video, we're experts on this, right? We have an RMS value, which in this case we can assume it's coming from a sinusoidal, pure sinusoidal wave of 50 hertz. So the relationship here, the maximum value we want, B max equals square root of 2 times VRMS. Okay, so in this case VRMS is 1200, so that calculation is going to give us 1697.06 volts. It's when you're starting with this and you're referring to RMS and max values, it's good to say this is max, Vmax, because it's referring to a maximum value. After a while, you drop that and you always refer to RMS values when you're talking about phasors, for example, and you always talk about maximum values when you're referring to time domain signals. That's a usual thing, but since you're starting with this, I recommend you explicitly say that this is referring to a maximum. It's not going to hurt anybody. It's just going to help you. So easy enough. B. So the problem says B. The instantaneous power absorbed by the load at t equals 1 millisecond. So the important thing here is that you know that these are phasors. These currents somehow are related to phasors that can be expressed in module and angle. But they represent actually the phasor domain representation of a time domain signal. So when we talk about instantaneous power, we're referring to current times voltage in time. As easy as it is, right? So now we need to define these two, okay, in order to get the instantaneous power waveform or expression. So For v of t, it's quite easy, right? It's simply v max. Let's use cosine as the base function here. 2 pi times 50, which is the frequency for this system, t, and we're gonna name this the angular reference. Always in a circuit like this, you have to define one of the variables, one of the voltage or currents, as the angle 0, your angular reference. Okay, so I'm gonna make it explicit here. Angular reference. Okay, you always have to define one as angle 0. And so V max, we already calculated it. And I of t, it's not that simple, right? We know that the current is, the current phasor, it's going to be 10 angle phi, right? 10 amps RMS, and the angle is phi. So how do we calculate that phi? Phi is going to be simply cosine to the minus 1, the inverse cosine of the power factor. Okay. So the important thing here is that we need to add something else, which is the inductive part. Since the angle of the voltage is 0, and this circuit is inductive, right? That angle is going to be negative, meaning that the current is going to be behind the voltage. So if we calculate this, the inverse cosine of power factor, that is always going to give us a positive number. That's why we have to add this. Let's make it explicit here. Due to the lagging power factor. So this is going to give us exactly minus 25.84 degrees. Okay, 84 degrees. So our phasor is essentially 10 angle minus 25.84 degrees amps RMS. But we are looking for the time domain signal. So the time domain signal is going to be 10 times square root of 2, right? Cosine of 2 pi f, which in this case is 50, times t, minus 25.84. So now here we have to be careful with the units. What we have here, it's the usual representation. However, when you do calculations, you have to be very, very careful, because this this element here, it's radians per second times second, which is time, right? And we're adding some degree. That doesn't make sense, right? So to make it make sense, what we need to do is transform this into radians, to some radians with radians. The same thing when you calculate cosine of some argument, that argument, it's either degrees or radians, one or the other. When you select on your calculator, I'm going to use radians or degrees, right? So in this case, we're going to transform everything into degrees. Sorry, into radians. So to transform this into radians, we simply multiply by pi over 180. So I'm going to add a note here saying explicitly, so you don't forget, okay? To transform from degrees to radians. Okay, and again, this is only for calculation purposes. So when you're writing down this, that's the usual thing. You only say 2 pi 50t minus 25.84 degrees, and everyone would understand this. But for calculation purposes, we need to add this. That's why I'm adding this explicitly. Okay, so now P of t, power, instantaneous power, let's not forget about this name, sorry. Instantaneous power. That's a function of time, okay? So this is V of t times I of t. Simple enough. We multiply those two things, we're gonna get B max, which is 1697.06 times 10 times square root of 2 times cosine of 2 pi 50 t times cosine of 2 pi 50 t minus 25.84 times pi over 180. Okay, that's the function in time. And now the problem is asking what is the instantaneous power absorbed by the load at some particular time. So we simply evaluate this function, right? T equals 1 millisecond. That means 1 times 10 to the minus 3 seconds. We evaluate this. That means that we, instead of using T here in your calculator, with your cosines using radians as an argument, you're going to put T equals 1 milli, right? Or 1 times 10 to the minus 3. So if you do this calculation, to avoid putting all this on the calculator, I did it already. So this should be 22,612 watts, which it's equal to, I'm gonna explain this already, 0.612 kilowatts, right? That's a usual thing, especially for power. If you wanna move into a power career later on, you should feel comfortable with kilowatts and also megawatts. So we're talking about thousands of watts, or we're talking about of millions of watts. Those are the usual magnitudes in when we're talking about power in the sense of transmission distribution. Now if you move into circuits, for example, design of circuits, chip design, the magnitudes are going to be in the order of milliwatts, okay, or even less than that. Microwatts can be too. Milliwatts is more common, by the way. But just feel comfortable with those things, especially with Dr. Pulgar. He comes from a power standpoint, so he's always going to be talking about kilowatts, megawatts, megabars, etc. Okay, then we have answer. This is then, just to put a mark on this, this is the value of the instantaneous power at one particular time. If you have already watched all the other videos, you know that the instantaneous powers is something like this. So we're pointing out at one specific point in time. So that's about it. Okay. Okay. Next, move on to the next one. What do we have here? This one, okay. This one is okay. Then it's asking for the apparent power supplied by the source. So now it comes, we're getting into AC power definitions, right? So let's do a recall here. Recall. The most basic definition, let's do a parenthesis here. Parenthesis. S, the definition of complex power is V times I conjugate. We're using phasors, a phasor definition. Okay, so what is V and what is I? Is the voltage and current at some element. So if we're referring to the source, then it's going to be the voltage at the source and the current that the source is delivering. If we're talking about the complex power at the load, it's going to be referring to the voltage at the load and the current delivered at the load. In this particular circuit, is simple enough such that the voltage at the source and the voltage at the load are the same, and the current given by the source and the current driven by the load are the same. That's not the general case, right? So my recommendation whenever you're facing power calculations is ask this question: what is the power, or what is the element that I want to calculate the power on? Is it a load? Okay, I'm going to calculate voltage at the load, and I'm going to calculate current at the load. What voltage and what current? The phasor, okay, the complete phasor with module and angle, okay. And once I have that, then I can do this simple definition: V times I conjugate, okay. This is going to give you, of course, a complex number. As any other complex number, it can be expressed in polar form. So let's call it the module and angle. Let's call it phi. And it can be expressed in real and imaginary part, okay? So this one, the module, it's called the apparent power. And it's measured in VAs, or volt amperes. This one is called the power angle. And as any other angle, it's in degrees or radians, okay? P, the real part of the complex power, it's called the real power, real or active power, and it's measured in watts. And finally Q, it's called the reactive power, and it's measured in volt amps reactive, okay? And of course there are multiples of this. For example, when we talk about apparent power for high voltage stuff or for big transformers and substations, we refer to kVAs or MVAs, okay? For example, for transmission lines, when you're looking at the transmitted power, then you're going to be referring to kilowatts or even bigger, megawatts, okay? For reactive power, again on big systems, we're going to be referring to kVArs or megavars, okay? That's the usual thing, again in the context of Professor Pulgar. If you move into the other part of it, when we're consuming very low power, then it's going to be milli or micro volt amps or milliwatts or millibars, okay? That's a way, that's a dictionary parentheses in this thing. Okay, now let's calculate things. Now that we know all this, we're going to calculate the apparent power. So apparent power, let's use the definitions, okay? Once you are comfortable with this definition, then you can skip some things, and I'm going to give you some hints on that. So V and I, we already know, right? So S complex, it's going to be V, which is 1200. Again, we have to use the RMS values, angle 0, times the current, which is, we said 10, angle minus 25.84 degrees, and this is conjugate. What does the conjugate do? Simple enough, it only changes the imaginary part. It reverses the imaginary part. What that is going to do to the angle, it's going to make it positive. Okay, so that would be it. And now we need to calculate this. You should be already familiar with these calculations now on your calculator. So you should get to the same values that I got here. So 1200 angle 25.84 degrees. or in real form, in rectangular form, is going to be 10,800.17 plus J 5.230.31, 5,000.31. So to answer the question, we calculated everything, right? It's not difficult. It's just a complex calculation, right? It's a complex number calculation. So once we get that, we know that this calculation is going to give us a complex number that can be expressed in polar form, or it can be expressed in rectangular form, right? And now we're going to answer the question. The apparent power would be the module of the complex power. Okay, so this in this case will be 12 kVA. That's it. That's how we answer the question. D says the reactive power supplied to the load. So again, even though we're using voltage and current at the source, this particular circuit is simple enough that you can use the same voltage and same current because both have the same. It's just a two-element circuit. In general, for example, the problem on the homework, then you have to calculate more voltage and currents, which you are able to do, but it's simple enough. Once you are able to calculate voltage and current, then you can calculate power. Use the definition and you're never going to get lost. So we calculated this. Q of the load. What is Q of the load? Well, it's this one, right? Let's put it in red. This one, it's going to be Q load in this case, which is going to be, I'm purposely going to say plus 5,230.31. I need more space here. Bars. Okay. And why did I put this positive sign? Because at the beginning we said the circuit, it's inductive or it's lagging, right? And how is that represented? Inductive means positive reactive power in loads. So the load, it's consuming reactive power. That's the way it goes. If it's capacitive, so if the load is capacitive, then this, it's going to be negative, always, okay, for loads. That's a convention, it's called the passive convention, okay. Inductive loads consume reactive power. That means that reactive power, when we calculate it at the load, is going to be a positive number, while capacitive loads inject reactive power. That's kind of weird. We have a load that is injecting power, but that power is reactive. Those are the things that I hope you ask professor in class, okay? But inductive means Q greater than 0. Capacitive means Q less than 0 on loads, okay? On loads. That's kind of the takeover here. So we already answered the question here. Let's put it here to make it organized. Q load, it's gonna be then 5,230.31 bars. And then it's asking for the load impedance. Okay, great question. What's the load impedance? How can we know based on power or based on current? Then E is going to be Z load. So again, load. Load is simply a way to represent voltage and current relationships. Okay, So we know Ohm's law, V equals Z times I. Now in AC, all those are phasors. So we can rearrange this equation and say, okay, it's going to be the voltage at the load divided by the current at the load. That is going to be the impedance at the load. So it would be 1200 angle 0 divided by the current, which is, we have it up there, 10 angle minus 25, 84 degrees. We do this calculation and we should get a complex number, of course, right? A complex number. That complex number is going to be 108.00 plus J 52.30 ohms. And I'm going to reiterate this. Whenever we talk about voltage and currents, see that I'm always referring to them as the polar form. Why? Because I want to see this value, the module, the RMS values directly there. So it's easy to understand if I'm telling you this current is 10 angle minus 25 degrees. You know that 10 amps is what I'm going to be measuring with an amp meter. However, if I'm telling you the current, it's 10.52 plus J 5.23. You have no idea what's the RMS value that you're going to be measuring. Okay, so it's just a convention. Again, it's an equivalence, but it's a convention. Same with impedances. Impedances are usually referred to in rectangular form. And here we see the real part, which is related to a resistor, and the inductive part, which is related to an inductor. Why? Because it's a positive reactance. It's a positive X that can only come from a J omega L, right? It cannot come from 1 over J omega C. No way. We don't have negative capacitors. So what this is implying on this problem is that this load that it's drawn as a box, it's actually a resistor with an inductor. Okay, that can be calculated based on that impedance that we calculated. I encourage you to calculate the R and L values related to this impedance for that frequency of 50 hertz. Okay, so we have that E, and finally F. F, it's asking for the complex power supplied by the source in polar form. We already calculated that, right? So let's move that result up here. The complex power, S, it has module and an angle. And it's explicitly asking for this in polar form, right? So we would say that's the answer. S equals that. Okay. So I think that finishes this problem. I think it's very simple circuit. It's a very simple circuit, but it's meaningful in the sense of the definitions and the use of power. So I hope it was clear for you. Revisit it if you need to, and you're always welcome to contact us for any questions that you may have. Thank you.